Hello everyone and welcome to the third session of this cost action meeting. Today we will have four speakers. It's Olga Smirnova, Thomas Pfeiffer, Lars Madsen and Agnes Vibok. And you can ask questions already during the talk in the questions and answers panels. And after the talk we will have 5 minutes each to answer the questions. I will pick the questions you have asked and read them to the speakers. After this session, you will also have the possibility to meet the speakers in the Meet the Speaker session. So if anything has not been answered sufficiently for you, or you want to discuss further, you can meet the speakers there. So I would like to start with the first talk, which is given by Olga Smirnova from the Max Born Institute and the Technische Universität Berlin. And her talk will be about efficient chiral light-matter interaction challenges and opportunities. So with that, I would like to give the word to Olga Smirnova.
Thank you very much, Eva, for the introduction. And I will start sharing screen at the moment, and I have 35 minutes, right?
Yes, exactly.
Okay, I will talk about efficient dynamical approaches to chiral discrimination. And first of all, I would like to thank my collaborators and friends. My collaborators from Haifa, Oren Cohen, Ofer Nefert, Trieste, Pierre de Clever, and especially important contribution from my brilliant postdoc, David Ayuza, and brilliant PhD student Andres Artanes, who have made important contributions to this work, and Misha Ivanov. These all people are from Berlin. So you probably all know what chiral molecules are. They are just like my right and left hands, two non-superimposable mirror images of each other, and no matter how I rotate my right hand, it will never look like my left hand. And what is right for me now looks like left for you. Left and right molecules are called enantiomers, and the talk today will be about the ways of distinguishing enantiomers with light. Chirality is a lot of fun, and probably because in our everyday life we constantly use chiral objects and tools. And you see some in here. The one on the left is Archimedes screw, probably the oldest chiral invention, and it was used in ancient times to sorry, it was used in ancient times, and it is still in use now. And as water rolls down, it rotates the screw. So the other device is also, of course, well known, and the principle also known to you. And the main chiral structure, as you can see from these pictures, is a helix. And the basic function of chiral device, as you can also see from these pictures, is to convert in-plane rotation into the motion orthogonal to the plane of rotation. And as I'm trying to picture this, my finger traces helix, which is a basic chiral structure. So how do we probe chirality? In macro world, we can take chiral object, bring it to the mirror, look at the mirror, compare with the mirror image, and decide on the chirality. And this principle I will call chiral observer. But chiral recognition can also be based on the interaction between two chiral objects. For example, our left and right hands. The proper handshake requires enantiomers of the same handedness. If we received a proper handshake, we know that our partner used the same hand, enantiomer of the same handedness. So this principle, we used the chiral reagent. Chiral reagent interacts with two different enantiomers differently. And the basic reason for this is the difference in the shape. Chiral light is also a chiral reagent. It interacts with left and right molecules differently. Indeed, chiral light, which is circularly polarized light, when it propagates in space, the electric field vector traces helix in space. And helix is chiral structure. So absorption, as well known, is slightly different in left and right molecules. And switching chiral photonic reagent, which is a chiral light, switching the light helicity changes the sign of this difference. However, the chiral light, which is helix in space, is poor chiral reagent because its interaction with chiral molecules is weak. And it's weak because the pitch of the helix is much larger than the size of the molecule. The pitch of the helix is equal to light wavelengths, and it's few hundred nanometers at least for IR UV light, and up to 1,000 nanometers. And molecules are, for small molecules are about 1/10 of the nanometer, and they are too small to fill the pitch. So, since the chiral photonic reagent, natural chiral light, is very inefficient, we need a better way. So, there are two roads to efficient chiral discrimination with optical fields that we can take. First one is to come up with the approach in which we would completely do not rely on light's chirality. And as you will see, on this road, we will need chiral observer. The second approach is to substitute inefficient chiral reagent, which is light helix in space, by efficient chiral reagent, which is light helix in time. However, observables along these two roads are completely different. But before I tell you about this, we need to remember how to characterize a chiral object. And to introduce the characterization of chiral object, let me use my favorite chiral object, which is a cow. So what makes cows chiral? It's the way they chew. About 100 years ago, prominent theoretical physicists Jordan and Kronig published a paper in Nature in which they explained that cows were chiral. So, as the cow chews, the jaw of a cow makes a rotating motion, but the foot goes in the direction orthogonal to the plane of rotation. And as you can see, there are two fundamental directions involved into this process. One is the direction of foot, which is characterized by vector J, a vector of foot, and another is a rotation of a jaw, which is characterized by the angular momentum. And angular momentum is a pseudo-vector. So what fundamental chiral observable does, it just takes these two vectors and combine them into a number. And this number is a scalar product of J and L, and in fact, it is a pseudoscalar. Pseudoscalar is a sign scalar. It's ideally suited for characterizing chiral systems because it changes sign upon reflection. And also because orbital momentum is a pseudovector. Pseudovector can be represented as a vector product of two vectors. Therefore, basic chiral measure can be represented as a triple product of vectors. And you will see a lot of triple products in this talk. So it's all wonderful, but there is a catch. The problem is that in the experiments, we do not really measure pseudoscalars. We measure scalars because we measure cliques. So the question is, where is a pseudoscalar? Where is a chiral measure in a clique, in an experimental clique? And to answer this question, let us consider the oldest probably technique of chiral discrimination, a traditional absorption circular dichroism. So, and in this case, we use the helix of light, and in this case, left circularly polarized and right circularly polarized interact with the chiral molecule, and we looked at absorption. Absorption is scalar observable. Absorption is a little bit different for left circularly polarized and right circularly polarized light, and this difference in absorption is a scalar. But the scalar is in fact a product of two pseudoscalars. One comes from the molecule and another comes from light. So the trick is that chiral reagent, second chiral object, is needed to hide molecular pseudoscalar into a clique, into a scalar. And of course, we can also name explicitly molecular pseudoscalar and light pseudoscalar. Molecular pseudoscalar is a scalar product of dipole, electric dipole moment and magnetic dipole moment, and the light pseudoscalar is optical chirality. So this quantity scales as a ratio of molecular size to the wavelengths, and that is why it is small, and that is what we would like to change. Okay, and then the question is, can we measure something else but scalars? For example, we can measure vectors, and there is a technique, photoelectron circular dichroism, which takes the circularly polarized light and ionizes the molecule and measures the electrons. Although we still measure cliques, we detect these cliques in different directions, which means that we measure vectors. And the relevant observable here is a photoelectron current. So this current flips direction if we swap molecular handedness. It's a purely dipole effect. Light chirality is not needed at all. And for that reason, one can get very strong signals. So the question is, where is the chiral reagent? So the answer to this question is starts on this slide. To measure a vector, we need to combine molecular pseudoscalar with a pseudo-vector. So in all techniques in which we use light to probe chirality, this pseudo-vector comes from light. So for example, in case of circularly polarized field, it has two components of polarization orthogonal to each other, and the vector product makes a pseudo-vector. And this pseudo-vector actually defines the direction of chiral response. Now, to complete the measurement, we need to provide the setup, provide the two detectors which determine the chiral lab frame of the observer. So in this case, the chiral lab frame of the observer is determined by two vectors, E1, E2, and additional detector axis. So what we get is that chiral reagent is substituted by chiral observer. Now back to photoelectron circular dichroism. Photoelectron circular dichroism, the light pseudo-vector is exactly the vector product of two components, as I just showed to you, and molecular pseudoscalar is given by the vector product of the photoionization dipole matrix element and its conjugate times the photoelectron momentum in the continuum. And this is a triple product. Triple product, molecular pseudoscalar, which is extremely strong because it doesn't involve magnetic interactions. And what we can see is this is the expression for the observable photoelectron current in photoelectron circular dichroism. And measurement scalar is a projection of this current onto detector, and measured clique is the result of this projection. So this measured clique is a product of molecular pseudoscalar times set up pseudoscalar. So set up pseudoscalar is a vector product of components of the circularly polarized light times Z, detector axis. So as you can see, in dipole approximation, of course, circularly polarized light does not have enough vectors to form its own pseudoscalar. And therefore, it has to borrow one vector from the detector to collectively form a pseudoscalar. So this pseudoscalar is not light pseudoscalar. This is combined pseudoscalar of the setup. What is interesting that Chiral Observer, the principle of Chiral Observer, can allow you also to measure tensorial quantity, not only vectorial, but also tensorial quantities. For example, in the case of circularly polarized light, the field has a symmetry in which it can define a plane, a signed plane, oriented plane. But you can use a field which has much lower symmetry, such that it cannot even define the direction of rotation, such as the field shown here. It's Lissajous figure shown here. It has first fundamental along y-axis and second harmonic along x-axis, so two orthogonally polarized colors. This field was proposed and employed in these publications. And the trick is that it changes the direction of rotations twice per cycle. And therefore, on cycle average, it cannot determine the polarization plane. But this is not a problem because we can borrow two axes from detector, and measured clique will be again molecular pseudoscalar times setup pseudoscalar. And setup pseudoscalar will be a vector product of two field components times the detector axis and times the other scalar product of the field along y direction and detection axis y. So which means that in this case you will have to make tensorial measurement resolved on axis z and y. So let me give you another example of how Chiral Observer can be useful, and it can allow you to resolve the chiral dynamics in bound states. I just told you that we can resolve photoionization dynamics, but if we look at photoexcitation and we use circularly polarized light short pulse to excite a superposition of two states, then we can induce dynamics. So what kind of dynamics we induce? I will show you a movie of the dynamics which is excited in this case. So this vector that you see is a polarization vector of polarization of induced polarization that we induced in the randomly oriented ensemble of chiral molecules. And what you see that first we see planar excitation, but then very quickly it is converted into a helix. So analytically, what you can show is that this induced polarization, the vectorial quantity of interest in this case, is given by, again, a product of molecular pseudoscalar, which is a triple product of three dipoles involved into these transitions, and light pseudovector, which is the same as in PCD, vector product of two polarization of circularly polarized light. So this induced polarization is chiral sensitive and molecule specific. It tracks coherence, electronic and vibronic, and it leads to macroscopic dipole, which is orthogonal to pump polarization, and it oscillates out of phase in opposite enantiomers. Let me see how much time I have. I guess not so much. So let me conclude regarding the observer that Chiral Observer is extremely powerful concept, and it already unites a family of different techniques, very beautiful techniques, such as PCD, PXCD that I described, enantiosensitive microwave spectroscopy, and dipole high harmonic generation, which can also be used to detect chirality. Importantly, that it allows you to measure vectorial and tensorial observables, but you cannot measure scalars. So scalars are extremely important because scalars allow you to perform manipulations, enantiosensitive manipulations, because you can control populations in the molecular levels. So I'll tell you how we can measure, how we can induce enantiosensitive scalar signals without resorting to magnetic interactions. So what I show now are is the movie of how the electric field polarization changes in space for a standard circularly polarized light. And if we apply dipole approximation, then we will see this. So you see, helix is completely lost, light is not chiral. So if we want to have light chiral and dipole approximation, we would need to introduce light which is chiral in such a way that it's chiral locally. And this is the example. So what you see here is the electric field vector, red, of the light, of synthetic chiral light. And this electric field vector traces chiral figure in time. And in space, it is located here all the time on the same point. And what you would like to construct such a light in which electric field vector will trace any chiral figure. It doesn't have to be helix. And also does it not only in one point, but in many points of the space synchronously. And this means that this helix or any other chiral structure would need to maintain its headliness everywhere in the interaction region. So then we'll have an anti-sensitive optical response already in dipole approximation, and it can be controlled by controlling the temporal structure of light. So it's of course a great idea, and to bring this idea to life, we need to answer the following three questions. How to characterize the handedness of this field mathematically, what would this measure reflect physically, and how to generate locally chiral field practically. So let's start with the first question. To characterize the handedness of locally chiral light which is chiral in electric dipole approximation, we introduce mathematical apparatus of chiral correlation functions. So the idea is that we take 3 snapshots of electric field vector as it evolves in time. And then we construct a triple product of these 3 vectors. Then we average over time, over period, to make sure that handedness remains on average. So if the triple product from 3 snapshots is non-zero, it means that we have traced a chiral trajectory. And if it maintains over the period, it means that we have a chiral Lissajous figure with definite handedness. So in frequency domain, it's a triple product which have such a form. And from here, you see that non-zero triple product requires 3 non-complanar frequency components. So now what does it mean physically? Physically, this describes the interference between 2 pathways which go from state 0 to state 2 in this 3-level system, and describe enantiosensitive absorption by synthetic chiral light, enantiosensitive absorption due to synthetic chiral light into state 2. So enantiosensitive absorption, as I told you, it can be described by the product of molecular pseudoscalar times light pseudoscalar. And let's compare this enantiosensitive absorption for standard light and synthetic chiral light, because it will help us to understand the meaning of this figure, of this creature. So the molecular pseudoscalar in standard chiral light, it's magnetic dipole vector times dipole. And for synthetic chiral light, it's a triple product of the dipoles involved into these transitions. And light pseudoscalar, here optical chirality, you can think of helicity, it's probably easier. And in case of synthetic chiral light, it's H3. This third order correlation function. So third order correlation function replaces optical chirality and characterizes the strength of chiral optical response to synthetic chiral light. And of course, to everybody who is familiar with coherent control, it's evident that by changing relative phases between these frequencies, we can control an anti-sensitive absorption into state 2. And it also means that handedness and the anti-sensitive absorption are controlled by these phases, just because we control the temporal structure of the Lissajous figure. So how we can generate such field? Actually, we can get away with just two colors, and we can consider a field which is elliptically polarized in plane y-x and frequency omega, and linearly polarized frequency to omega in along z-axis. And this field traces chiral Lissajous figure in time, and that is how this figure look like. Red is again electric field vector, and this is a chiral figure. So I told you that the correlation function of third order requires 3 frequencies, and here we have only 2, which means that this correlation function will be actually equal to 0, but this is not a problem because there are higher order correlation functions, and their meaning is that they characterize handedness of higher order multi-photon process. For example, we can consider the multi-photon, we can consider H5, correlation function of the next order. So it describes the following process. It's an anti-sensitive absorption from level 0 to level 1. And it describes the interference of 2 diagrams shown here. In the first diagram, we absorb 3 photons from X component of omega field and emit 1 photon from into Y component of the field. So this pathway leads to induced polarization, which is, according to this corkscrew principle, is along Z direction, because we imparted rotation XY and response in the Z direction. And this Z component of polarization is at frequency 2 omega, and it interferes with the 2 omega field, with the polarization from the 2 omega field. And this interference leads to chiral signal, and of course controlled by the phases between 2 omega and omega fields. And this extremely simple and simple expression typical for interference shows you how we can control the outcome of the absorption of the 2 omega field. Now, the same, of course, applies to the emission, and here you see the emission of second harmonic, but it also applies to emission of all even harmonics. And here is a specific way how to realize, at least one way how to realize this field in the lab. And what you see here is a non-collinear setup. There are 2 beams, each carries the linearly polarized field in the plane of the screen, and orthogonally polarized field, which is linearly polarized orthogonal field at the frequency 2 omega. And by changing the phases in between omega and 2 omega field in each beam, we can control both local and global handedness of this field. And probably I do not have time to tell you about details. You can ask me during the question and answer session. I'll only show you probably the slides for high harmonic generation in propylene oxide, and this is already far field signal, because I guess I don't have time for near field signal. So what you see are the red and green harmonics. On the vertical axis is harmonic number, harmonics from 30 to 44. On the horizontal axis is divergence angle in degrees. Blue harmonics are not enantiosensitive, they are odd harmonics. Enantiosensitive harmonics are red, and in right molecule and in left molecule we have completely different results. As you can see here, red harmonics completely disappear in left molecules and they are quite strong in the right molecule. And here you see more quantitatively what's going on. So here are even harmonics, and you see that green is a total signal for right molecule, S is total signal for left molecules, and the circular dichroism is the typical figure of merit, is the difference between the intensity in left and right molecules divided by the sum. And you see that circular dichroism reaches its, divided by the sum, and the circular dichroism reaches its highest value, 200%. It also can be controlled in the full dynamical region, full dynamical range, from 0 to 100%, just by changing relative phase between omega and 2 omega fields. So what I would like to say as the conclusion to the second part, to efficient chiral reagent, is that we fully expect the family of light or electric fields, chiral reagent, which are chiral in the electric dipole approximation, to appear. And there are already 3 members in this family: synthetic chiral light I just described. There are chiral configurations of electric fields explored in this beautiful paper, and there are also chiral configuration of microwave fields and already demonstrated control of enantiosensitive population in rotational states. So with this, let me conclude, and I am open to questions. Thank you for your attention.
Thank you, Olga, for this great talk. And we indeed have already a question by Hans-Jakob Werner. He is asking, what quantitative uncertainty would you associate with your prediction of 200% chiral effect in propylene oxide?
Quantitative uncertainty, I don't know what you mean. Do you mean how accurate our methods are? So what I will tell you that our methods are not accurate. And therefore, what I expect is that the phase, relative phase for which we see the best signal will probably be different in the experiment. And however, what I would like to state is that one can always find a phase for which in the regime that we proposed of a weak 2 omega field and strong omega field, you can always find a regime in which you will be able to kill signal in left enantiomer and enhance the signal in the right enantiomer, and that requires tuning of the relative phase and relative intensities of the field constituting the light. Basically, epsilon, the ellipticity of the omega field, and the omega field which is formed once we have 2 non-collinear omega fields, and the strength of 2 omega fields. So these are 2 competing things, and you can reach by tuning them, depending on the molecule, parameters can be different, but such regime can be achieved.
Mm-hmm. Thank you. So are there any other questions? Yes. So again, Hans-Jakob Werner, does this imply that 200% effects can be expected in all chiral molecules?
That would be such a big statement to say. I think I'm looking forward to the experiments, and I would expect that high circular dichroism can be reached.
Mm-hmm. Thank you. Any other questions? I don't see any popping up so far, so maybe the audience still has some. I have one question myself. So in your results you showed for propylene oxide, I guess these were theoretical calculations. So I wanted to ask, what were the methods you have used to calculate this?
Yeah, I will show some of the results. In this particular work, we used our. Am I still sharing screen or not?
No.
Okay. Okay, so in this particular work, we used the multi-channel high harmonics codes that we developed in my group over the years, and they combine basically factorization of ionization, recombination, and propagation steps with as accurate inputs into each step as possible. And for recombination, we used in this particular work, it's not always that we use this setup, but here we used the approach of Pierre de Clever because it is well documented that for chiral photoionization, it gives really good agreement with the synchrotron experiments. So these are photoionization dipoles computed with static exchange DFT, and bound and continuum states expanded into a multi-center expansion for B-splines and spherical harmonics. And here you see a cartoon of the expansion and the large radius, about 30 atomic units. These are for continuum states. And the parameters are the 20 angular momenta and 100 B-splines. And for the bound states, there is different small off-center expansion, basically these little spheres, and these are the parameters. And of course, you need a low amount of angular momenta in this case. So this is the comparison, a very nice comparison with the experiment, and because we need it actually for the reverse process for recombination, we use this. For the ionization, we use TD RIS code of Sergei Pachkovsky and Michael Spanner, and propagation is treated using usual SFA stuff. So I guess this is in, yeah, and I forgot to show that we benchmark, yeah, and also we include many channels. I think we included A, X, A, B, C, and D channels, so 5 channels, including laser-driven dynamics between them. And we benchmarked it on the experiment of published by Raluca, Chiresha, and others in this publication. And so we managed to get a reasonable agreement, and based on this input, we then simulated what you see now for the results that I presented. But of course, the method is by far not ab initio, by far not first principles, and I do not expect it be quantitatively accurate, never expected, but I do expect that qualitatively it shows correct physics.
Mm-hmm. Thank you. We have another question by Jan Markus Dahlström. Did you consider phase matching of omega and 2 omega fields propagating in different directions to have polarization in different planes?
We considered macroscopic propagation and all phase matching effects, yes.
Okay. I guess that answered the question. If not, you have after the session still possibility to discuss with all the speakers, I hope. at least there is the Meet the Speaker session afterwards, and we have to move on. The next, thank you very much, Olga, for your great talk.
Thanks a lot for questions and your interest.
And our next speaker is Thomas Pfeiffer from the Max Planck Institute for Nuclear Physics. And he will be talking about the electronic response to attosecond excitations and steering it with strong fields from the infrared to the extreme ultraviolet. And with that, I give the word to Thomas Pfeiffer.
Yeah, thanks very much, Eva, for the kind introduction. I somehow have to find out, sorry, sharing how to start it. It worked before, but now something changed, of course, but I think that should be almost it. So, is this full screen now, I hope?
Yes, we can see it.
Perfect, very good. So, thanks very much, as I said. And thanks to the organizers for setting up in these crazy times this remote meeting, and with lots of back and forth until we converged on this. This is great. So I would like to talk about the electronic response to attosecond excitation and steering it with strong fields throughout different wavelength regimes. And before I start, I would like to talk a bit about some fundamentals in the title. What is a response function? So what is this? Consider a system either at rest, ground state, equilibrium, and consider some perturbation, some kick you give to the system, a delta-like kick, which could be a force. This can be anything really, electric field, some kick in the metric tensor of space-time, whatever, you name it. And this kick sets off then some response, as you can see it down here. And this response function now, this is actually key in a lot of things, and also, of course, enters experiments. So it allows you to think about the system. This contains a lot of information about the system. And the nice thing about it is if you consider in particular electromagnetic responses, this is easy to measure in particular. And so I will talk a little bit about how this goes. So for atoms, let's start simple, two-level system here, an atom model. You have a delta-like kick that interacts with your atom, with your two-level system, and it sets off a response. And a simple response in an atom is just this coherently decaying dipole that is actually created by coherent superposition of your ground excited state in this delta-like coherent pulse. And the pulse will actually be modified by propagating through a medium consisting of many of these atoms. And if you take a Fourier transform of this time-dependent dipole into the frequency domain, the dipole in frequency, you can already see if you take the imaginary part of what you get, it's a complex function, the Fourier transform, take the imaginary part, it will be showing you this Lorentzian line shape, as you know it from typical lifetime broadened resonances, if you can fully resolve them in your spectrometer. And why is that? This is because the dipole response is connected to your susceptibility, macroscopic property, via the polarizability of the medium. And the susceptibility in turn is basically linearly proportional for thin media to the refractive index change. And the imaginary part of a refractive index is just giving you the absorption. So if it's constant, it's an exponential type absorption Bayes' law. So very simple. And this is in fact used in a lot of places, and it's also very old. So this has been discovered in a way, if you want, this absorption spectroscopy of shining light through a medium and looking at what misses in the light spectrum. This is an old phenomenon. So Wollaston, Fraunhofer, they looked at the sun, in fact, the solar atmosphere as transmitted by rays, visible light from the sun, and they could see that there is light missing in the spectrum. So this looked in a way like this, of course, not so well resolved in the beginning, but you could identify lots of dips in there, which people later assigned here, Kirchhoff-Bunsen at Heidelberg, to the elements. This came actually later. So lots of fundamental physics came afterward. As you know, this is the beginnings of quantum mechanics, characteristic lines. And of course, these characteristic spectral line positions, it's not all, there's line widths. As I've just shown you, the lifetime gives rise to width. And there's even more, there's different shapes of these lines. They can be Lorentzian if you just have the lifetime broadening, or Gaussian if you have like other effects, for example, Doppler shifts, or Fano if you have an interference of a discrete state with a continuum of states, then this even changes the symmetry of this line and so on. And all this basically enters into various spectroscopy approaches in chemistry, which are used in chemistry. So chemistry deals with elements and compounds, composition, structure, but in particular, the changes that happen in these things. And so, of course, people have been using a lot of methods to look at changes in molecules, for example, with these infrared spectra, or also then also with XUV X-ray spectroscopy, XAs, XANEs, and XAFs, all kinds of variants of this, to get not only vibrational sensitivity in molecules for vibrationally or infrared active molecules, but also to directly look at elements and get characteristic fingerprints of the elements by looking at core transitions. And so if you could say, basically now what chemists do, you can look at everything, all of this, so you can look at vibrations, electronic things, and really it starts with physics, you can say. Chemistry starts with physics on the level of atoms. So this is what molecules are made of, and on the fundamental level, in the end, all the changes start on the level of atoms, or actually subatomic with the electrons. So a question or an ultimate goal could be to control now atomic molecular energy levels to get full control, you could say, of chemistry. And by the way, this is already done. So what catalysts have been doing all the time is really playing around with molecular energy levels. Of course, typically not in time, but of course they shift also the barriers of transition states and allow chemical reactions to take place that would otherwise not happen so quickly. And in a way, what we are doing now in a sort of chemistry 2.0, so when you say we, the entire field, of course, wants now to go to chemistry on a subatomic level. So to employ the coherent motion in a way of electrons, yeah, directly to drive chemical reactions, to also monitor these things that are going on, as we've heard already nicely in talks before. So to set off some motion of electrons and to see that propagate on a very fast time scale, this characteristic time scale of electrons with large energy spacings between electronic states throughout molecules. And of course, what one could think now, ultimately, of course, it would be nice if we could not just use catalysts to sort of tune around energy levels in a static manner or slow manner, milliseconds or so, but really make use of these very fast and really well controllable agents, these light fields that we have, strong light fields. This is, and sorry for doing this, so this I modified, obviously. So here you can see electrons moving differently. Of course, now as you start to play with these level structures, you can, at different times, localize electrons in different places. And this is, of course, just an example. This could be way more complex, of course, if we would understand all the details. And so what we need to do is to get an understanding of spectroscopy in basically the strong field limit. So you want to see what happens if you now not only look at response function that we're doing all the time, linear responses just to weak light fields. An attosecond pulse actually is a weak light field. But now what happens also if, say, either the attosecond pulse gets more intense, or if you have additional fields, laser fields of different various frequencies, polarizations, and intensities to act upon excited states that you create in your system, which can really be atoms, molecules, solids, liquids, whatever, you name it. And very often, so what is closely related to these questions is this entire field of attosecond transient absorption spectroscopy, which people have pioneered here. And there's now lots of people, actually, this is not listing all of them. I tried in the beginning, but at some point there's a long list now, in fact, of people who are doing this. Transient absorption, but it's not exactly always asking the same questions. Very often, transient absorption wants to just follow the dynamics after a pump event. You pump a system. This is what actually transient absorption spectroscopy very often does. You pump a system and you probe it at different times to follow the natural evolution of the system. So measure, extract the natural multi or electron dynamics in the system for the field of attosecond transient absorption. Here we want to not just look at what the natural system is doing, but in fact, one key goal is to now modify these natural dynamics in excited states with laser fields of tunable intensity, so to get now multidimensional spectra, which could list intensity here, but it could be polarization, as I said, wavelength, all kinds of things, even pulse shapes of some quantification of parameterization of pulse shapes that you could use to understand what happens in these systems now as you drive them really with fields that not only perturbatively but strongly affect that dynamics. And of course, now you need to wonder what is basically the key elements of these modifications you do in strong fields to your response function or to your system, of course. This goes hand in hand. So then you look at resonance absorption in the time domain for the case of a weak excitation pulse and a strong pulse that immediately follows this excitation. This is one of the most simple cases you can imagine. Two very short pulses, short on the time scale of the lifetime. So the lifetime is supposed to be much longer than the time difference between the two pulses and also the time duration of each of these events. So consider this special case, very short modification right after the excitation and then a long lifetime. What then happens is really an energy shift. So I play this again, an energy shift of the strong pulse, which could be or it could affect the excited state, could also affect the ground state, doesn't matter. It affects the relative energy spacing over a certain time duration, delta t, the time scale, the time duration of the strong pulse. And this product of time by energy divided by h bar gives rise to phase shift. And this phase shift will imprint itself in this dipole, because this is just a matrix or the scalar product of excited state, ground state with a dipole in between. So you have this phase shift. And if you now do the same thing, you look at what the absorption spectrum would look like in such a situation, it's no longer just this lifetime broadened Lorentzian, but it looks like this Fano line shape, as I've shown you before, this very fundamental line shape. And it turns out you can prove that this phase shift here, delta phi, is related to the Q parameter by means of a very simple mathematical formula in this limiting case of short interactions very close to each other on the time scale of the lifetime. So this comes out, and this is one of the first things that now also in our group we measured this. So this is basically how these experiments proceed to convert your infrared or near infrared, near visible, it's actually a broad spectrum through the visible and near infrared pulse to the XUV. So you generate here attosecond pulses in this visible or near visible light field. Then you refocus both these fields over two mirrors, a toroidal curved mirror to create a focus and another split mirror where you have an inner and outer part which can move with respect to each other and create a time offset between these two pulses. Go through target cell here filled with helium to have a simple target to understand things, and then look at the spectrum and this entire broadband spectrum at once on a flat field grading spectrometer. And this is what the spectrum looks like, and in fact this is the changes now that happen as you move the time delay between the strong pulse and this weak attosecond XUV pulse. So you see the spectrum is changing. This is the experimental setup. I have to be brief here, what it looks like, just to give you a flavor. This is a home-built grazing incidence setup with a mirror here with this inlay in the middle you can see. And this is this home-built flat field grading spectrometer that we use. And with this, you can now directly take this three-dimensional data that I've shown you before as a function of time delay between the XUV and the near infrared pulse. You get a spectrum, an absorption spectrum. This is the photon energy of the spectrum you measure on your spectrometer. And what changes now in real time for us is the intensity. And you can see as you increase the intensity, lots of things change in these spectra. So you get a rippling pattern here at low intensities already, then you wash out this rippling and all the lines, in fact, at high intensity, because at highest intensities, at some point, you could just simply ionize all these excited, doubly excited states. So these are, I should say, these are doubly excited states in helium that you now put under the influence of an intense IR pulse. And actually, this is a thing you can now tune directly from weak perturbative effects, try to understand simple effects all the way to strong field effects. And it took us a while with lots of cooperators to go through these experiments and really to understand what is going on here and to make, to get the most out of this. So This is if you now make a cut just along the time delay axis, you say, just look at this 5 femtosecond time delay, so the near infrared pulse right after the exciting pulse here, and you dial up the intensity, and you see lots of things happening. So for example, this 2s2p, this main double excitation, this famous one that Fano also worked with in helium, this creates now, or this starts as a single resonance, but then it creates this doublet feature, and it diverges, as you know this from strong coupling. So in fact, it turns out this is a strong coupling effect between this 2s2p double excitation and the 2p double excited state by a laser photon. So this state is not directly visible from the ground state. There's a symmetry, even symmetry, just like the ground state is. So it's forbidden by dipole selection rules. You don't see it directly in the spectrum, but the laser, of course, the optical laser can couple these states and sets up this Outler-Towns doublet. And you see more, so you see also these phase shift effects where your Fano line shapes now get modified from the normal Fano line shape, as you measured with synchrotrons for a long time, to these symmetric profiles, Lorentz-like profiles, all the way into an inverted Fano line shape. So not up, down, oops, not up, down, but slowly down, quickly up. So this line shape gets inverted at high intensities, really by these phase shift effects on the energy of these states, as I've shown you before. So I'm not showing you the details because I want to go on with new stuff. So the dipole control model, this is in a way what I've shown you before, but this can be really extended. So here we just have again the free decay leading to an absorption spectrum. I've shown you so far if you have this pulse, the IR pulse, following right after the excitation to just create a phase shift. Of course, this is all not to scale, so the oscillations are much faster, you have to imagine. So this is just to see it. This we understood already from this simple formula before, but you can keep going and ask if you have now time delays, so longer time delays on the scale of the lifetime, so significant portion of the lifetime you send in the IR pulse much later, so that actually the lifetime plays a role. And it turns out, so this is what Alex Blättermann has shown in his paper here, if you now make a piecewise definition of your response function, where you say it oscillates freely after the excitation, and then at a certain time, tau 1, tau 2, it gets modified by a complex factor A. And then from there on has a different amplitude, scaled amplitude, and a phase, a different phase. You can in fact find a very simple analytical formula still for this case, where you still say, okay, at different time delays now I interact with the system, so the amplitude is changed, the amplitude and phase is changed at tau. This is basically then the formula that you get for the spectrum as a function of tau, so this can still be done. And in fact, all this understanding now, which is also cast in this paper here, which is a generalization really of this dipole control for early times that we had before, this has led to a lot of different things that we were able to do, ranging from really fundamental physics, so basically thinking about X-ray frequency combs, rubidium experiments, all the way into complex systems, or doing basically 2D spectroscopy now in the inner valence region, as we've demonstrated some time ago. And so these are just examples. I will go a little bit more into one of them, and then also completely new stuff that is not even on this. So what is a particularly interesting case of this control, this dipole control model, is also the dipole amplitude gate, which says this A factor is just 0. After the time delay tau, it switches off, the pulse basically is so intense, for example, it ionizes or it completely decoheres the entire wave function of the system, such that the response is 0 from there. And what this does, it creates a temporal gate in which only you can observe this dipole response. So basically you can directly look at a certain part of the dipole response with this method. And that's what we've done for the case of a resonance, this famous 60 eV or 60.1 Fano resonance in helium with our cooperators here, as you can see. And so we could reconstruct in time the build-up as a function of time delay from when you interrupt this resonance at early times and stop it. You have a broad resonance, of course. Short time, of course, corresponds to a broad spectral feature. And as you let this resonance build up in time, you get, in the end, almost this full Fano profile as you know it. And this was basically a calculation from many years ago, also in the group of Joachim Burgdorfer And this was basically reconstructed, almost directly measured by this method of this gating. And we also worked with Jidong Lin at Kansas State to do an analytic theory of this. And you can see both the analytic theory and the ab initio, of course, even better fits very well with the experiment. So this gating method really works nicely. And what was shown already in the morning also is that this is now basically a complementary approach to do and to measure these attosecond dynamics. So this was the paper reconstructing this Fano resonance directly from the outside, you could say, by the photoelectron that's coming out and is then measured or affected by the rabbit method and picked up in an electron spectrometer. This is basically looking at the electron coming out, and this method, as I've just shown, is the picture looking basically at the missing photons. So it's looking at the optical side of this same phenomenon, and of course then also allows to reconstruct this resonance. This was the dipole control model for the gate, but now I want to show you something which I've not talked before. So this is of course working with an analytic formula as long as you have these very short and this defined perturbations with some certain amplitude at a distinct time, which happens immediately, like a kick again. So it modifies the dipole at one time tau and only at that time. But what would you do if you would modify your dipole throughout a larger range of times in a longer time period? And you still, of course, that would drive your resonance states and stuff around in a complex manner and set up a complex strong field affected response. And the question is, of course, this gives rise to a complex spectrum that you can pick up in your experiment, but can you still see this time domain response function from such a complex spectrum? And so can it be recovered? Can the time domain complex dynamics of the dipole moment be recovered from only this spectral measurement in your absorption spectrum? And the answer is it can, and it's basically going again back to the roots to Kramers-Kronig relations. So what you can do is you can select in your spectral measurement that you have here, you select just the resonance you're interested in. So what happens around this resonance with the spectral filter? You do this directly on your data set, you select, then you get this spectrum of only that resonance. And if you then do a Fourier transform of this spectrum into the time domain, of course, you would say you don't have the full phase information here yet, because you only pick up the imaginary part of the spectrum, which is just a real number. So you do not have the phase underneath the spectrum, which of course there is. But what you can tell is this was created by a very short excitation, by an attosecond pulse. So what this means, if you take the Fourier transform of this, you know immediately, because that's what you get from the Fourier transform, a symmetric response, but you know the time. So since it was an attosecond pulse, you know there cannot be any response on that side of times, because before the attosecond pulse, there will be no response. This is basically Kramers-Kronig. So you say you throw this away, and if you throw this information away, then there is a unique way of what the response here has to look like in amplitude and phase. And this is then also working, not just for, of course, what Kramers-Kronig did for just a perturbative excitation of the spectrum, but even if you modify the response on one side, on the positive side of time delays, and pick up a crazy spectrum, you can still then use the same Kramers-Kronig principle to reconstruct your information on that side of this temporal response. And that's what we've done here, again, just testing in helium atoms, where we know ourselves, where we know the way now. Helium atoms, and you look at basically intensity increasing. So again, attosecond pulse, and perturb it at a certain time delay with an intense IR pulse where you vary the intensity. And now we focus really on this Outler-Towns doublet of this 2s2p resonance. And you can see this is what the spectrum looks like at different intensities now here. So this is corresponding to these white lines. And by using this Fourier method, you could directly recover the response in time, which is basically showing now the onset of such Rabi oscillations between two different doubly excited states at high energy. And you could compare this now to few level models or to a more rigorous simulation by the Burgdorfer group, and found out at which point does this few level simulation really break down. At what intensity is it still good? This is, for example, here, there still all the models work well. And at some point, the few level simulation breaks down because too many states get involved in these interactions with the IR pulses. Too many states get coupled and the few level model is no longer valid. And this creates these nice pictures where now, not just from a theory point of view, you can reconstruct this response function, but even in the experiment, just by this Fourier method, you can, at different time delays, see how this intense pulse now basically goes through your response and directly see this from the measurement. So without anything else, just the Fourier transform of your absorption spectrum. So as I said, this was this cooperation also that we did to find out more about it. For the last part of the talk, let me go into something else, which is not driving. Okay, there will be something where this will come back, but now let's look at what happens if we don't drive the excited states with an IR pulse. But if we really just want to make our lives simple, you could say, and just use a single color field, just use one frequency, one strong XUV field, because you could say this is even more well-defined. So you don't have different colors. Okay, at the end, this is what you want. You want to drive electrons in different states, but it's a more defined, well-defined case to just have a single strong pulse with one XUV, for example, frequency to couple such states. In the best case, of course, an intense attosecond pulse, which may soon actually become possible. So this is what I've shown you before, now all the time, attosecond pulse and an intense IR field to couple between all these states here in the excited manifold. Now what would be great is if you had an attosecond pulse to couple strongly just between the ground and specific, or at some point also a superposition of these excited states, but only with one pulse. This would be more well-defined. And if it's broadband, of course, then you could also do a lot. But let's start somewhere, and this can be done, in fact, now these experiments at free electron lasers. So you can have intense light in the XUV that allows you to strongly drive double excitations also in atoms, or also some more complex interactions you could do in molecules, of course, not just double excitations, molecules, also multi-electron excitations would be possible. So this involved moving basically our almost entire lab with many people to flash free electron laser at Hamburg. So this is flash. This is what it looks like in the experimental hall. Almost the entire lab, as you see, set up on the beamline 2 in the flash experimental hall. And this is what the insides of the chamber looked like. So there's the incoming beam of the FEL, creates in this target cell, again, can it create also, of course, ionizations? It's very intense, so you will see a plasma recombination light. And this is, in a way, a real-time movie of the plasma as the FEL pulses come in at 10 Hertz, unfortunately, at flash. And this is what the spectrum looks like at flash, also at this 10 Hertz rate, which is unfortunate. And as you may know, probably, the FELs at Hamburg, at least, not the nice Fermi FEL in Italy, but at Hamburg, you have this stochastically varying spectrum from shot to shot, of course, which makes the experiment a little harder, because you now cannot just measure single spectra and get the effects, but you need to accumulate over several of them. But then you see, okay, here's the helium absorption line again. If you look at this with the helium target, you see, and at higher intensity, you again see effects. Here, for example, the absorption dip is already washed out. So something is happening, and this can be now quantified. Let's first look at what we expect to have. So this is a model simulation for effects that would happen in helium for strong XUV driving. And so you would see, again, the absorption spectrum as a function of intensity. It does change from this Fano line shape where you see bright and it gets dark and then goes back to the background. It changes into a more symmetric line shape. You can also look at this in cuts here. Fano line goes and changes the Q parameter, and accordingly the phase, which this quantifies, changes the phase of this parameter. And you can also see in the simulation over time, so over a very short time, you modify the phase again by these energy shifts that I've talked about in the beginning, but now induced really only with the XUV pulse alone. So this is the energy shifts that you would create with the FEL. The nice thing about this is if you look at least here the model simulation, you would predict that you get for a short time basically an inverted autoionizing state where you have more electrons on the doubly excited state than basically in the ground state. Yeah? So in a way, you could think of even making a double excitation lace, but this is what the simulation predicts. Yeah? And it's also a very funny exotic state, like a hollow helium atom, 2 electrons bound, but outside, not on the inner shell where they are usually, but on the outer shell. And what this would mean now here for this model is that we start to drive, we are on the onset of driving a Rabi cycling of 2 electrons. This is basically what the strong electric field of this FEL would do. It would promote by correlation effects 2 electrons to the excited state and back. So if it's stronger, here we just see going up, not yet coming down. But long story short, in the experiment, we see really these effects of this changing line shape. As you can see here, Fano line at low intensities and at higher intensities, you get this more symmetric looking line shape. Again, Fano parameter Q is changing at different energies of your incoming FEL pulses. And this nicely fits to this simulation that I've just shown you. So we can say we are really starting to drive strongly this 2 electron double excitation. And this was a large corporation, people involved in this. I have to speed up a little bit, so I cannot have too much time about another nice experiment we did at FLASH, which is now really XUV pump, XUV probe, transient absorption spectroscopy in the gas phase, where we looked also again here in large corporation, but very essential was the one with Helmut Zacharias, Uni Münster, for the autocorrelator we used. So this autocorrelator is built into the FLASH machine that can be used by any user. And with this autocorrelator and scanning the time delay between 2 XUV pulses and looking at the absorption spectrum, you could already see here very quickly that in neon this time, you could induce a change of this absorption. Yeah? So where you have basically at some time delays, you have a high transmission through this sample, and another time delay, you have a lower transmission through the sample. And what you also saw is not just this overall effect in, say, the global absorption broadband over the entire FEL spectrum, which you can see is not so broad as your harmonic spectrum. If you have the supercontinua from the attosecond pulses, this is of course much nicer to have broader spectra for transient absorption. So for the FEL here, it's limited at the moment. It would be nice to have this also extended at some point. But what you could still see in that narrow spectrum is also resonance lines. And these resonance lines, which are actually due to a doubly excited helium. So you basically use 2 photons from the FEL to doubly ionize neon. And then from the doubly ionized state, you have resonances that you can see as imprints here in this absorption spectrum. These are these like lines. And another interesting thing that happened is this feature at very short time delays. So very close to 0 time overlap. You got a strange feature, which we first thought, okay, well, maybe this is just an error in the data acquisition, but then we zoomed in and took data again with finer steps and saw this feature is still there. So pump and probe, very close to time overlap. And it turned out we see these coherence effects that people have started in the early times of pump probe spectroscopy, also in the optical domain. We see this now with XUV pulses. So this is there. We also understand where it's coming from. It's in a way a plasma diffraction effect, which is almost a bit like transient grating effects already. And it comes from this coherent enhancement, basically, of 2 pulses. So we split, of course, each pulse is different from shot to shot, but the pulses on pump and probe, since we derive them from a split mirror, they are correlated to each other in intensity. So when we scan them across, you get an enhancement again in this time delay 0 region where you have this coherence artifact. This also works for the statistic pulses. And in fact, not only this works, but we have signatures of spectral interferences in the spectra that we pick up. So we really see if we Fourier transform our absorption spectra or our spectra of the FEL, if we Fourier transform them, we see as a function of time delay characteristic Fourier components in these spectra that indicate, even though it's the Sase fluctuating, statistically fluctuating pulse, we can identify spectral modulation signatures which correspond to double pulses. So this already works, and of course we're excited to keep going with this towards more like traditional two-dimensional spectroscopy methods as applied in the optical, in the IR, in the radio frequency, now with XUV and site selectivity at some point, of course. So for the last very few minutes I hope, phase control of real molecules. This is some other thing that we are currently...
There's only 1 minute left.
1 minute, sorry, then I will really be quick. Then it's just an outlook in a way, you could say, phase control of real molecules, large ones. Would all these methods with phase shifts and modified spectra apply also to much larger molecules? And there was an early experiment we did already, this in 2015 published, on a laser dye, where we modeled this very simply with just a molecular absorption band modeled with a set of Lorentzian lines. And just assuming now we dress these individual lines differently with our infrared laser. This was not done with XUV light. This was just with a near IR laser frequency only, I have to say, not XUV. You could get a measurement where you again see as a function of intensity, you change the spectral shape, and the simulation, just assuming this very crude toy model, would allow to reproduce these features, spectral features of the measurement. So this seems like it's working. And another thing that we are more recently did is now to do measurements in these aluminum phthalocyanine chloride complexes shown here, where we also do transient absorption now still in the visible and recover all these characteristic features that we know. So basically these hyperbolic features which show up in the Fourier transform as diagonal lines. In these spectra. So we are confident that we can soon do this strong field control and strong field spectroscopy. We can transfer this also to the liquid phase with this. With this, I'm concluding, I'm showing the people. This is actually the effort of a large number of people in the division. So this is a picture of our last group retreat when these things were still possible. Currently, they are not, of course. Lots of cooperators throughout the years that I also try to point out in places in the talk already. And for the FEL experiments, this is really a huge list of people with different institutions that I'm just copied here, the list of names and institutions on this slide. And with that, I conclude. I don't talk about this all again, so I just show you some pictorial summary of what I talked about. Absorption spectroscopy. It's really you can use this dive control model as a metrology tool of amplitude and phase of these strong field effects. After understanding all this, you can really use it to measure phase shifts. And after all, the phase shifts affect the electronic dynamics of these molecules. So this is what you can get out of this. You can do this with XUV light in atoms, but also with IR light in complex molecules. And we're continuing with this. And of course, the goal is to go towards really understanding and controlling quantum dynamics, and with all kinds of light in the entire electromagnetic domain to really control the full thing. This is the final goal of this. So thanks very much for your attention.
Thank you very much for your nice talk and all your interesting results. So we still have time for 1 or 2 questions. So far, I don't see any popping up. Maybe there still will be one question. I have a question myself. So for the Rabi oscillations of the doubly excited 2s2p state, you showed that the resonance changes from Fano to more Lorentzian. I didn't understand quite why this is the case. Could you maybe elaborate again a little bit on that?
You mean why it changes at all, or why it changes as a function of time delay also?
Why it changes the shape. So why is the shape changing from Fano to a Lorentzian shape?
Okay, so this is really this additional phase that you imprint on the dipole response. So if you assume you have no phase shift and just look at the dipole response in the frequency domain, it gives you always a Lorentzian line shape for a state where there is no continuum involved. So if you have just an excited stage which just decays basically by, say, for example, fluorescence, emission of a photon, then there is no phase shift naturally, and it will always be Lorentzian. As soon as you now create a phase shift, either by laser or by putting this isolated state in the continuum, this is what Fano situation, then a phase shift is created, and then it turns out the Fourier transform then directly reflects in one of these asymmetric line shapes. So basically what Fano did is now, in a way, you could say it's general whenever you have a phase shift involved by whatever means, whether it's the continuum or a laser that shifts states in energy around you pick up this additional phase and it reflects in this Fano profile, Fano line shape as a background. So.
Thank you. So we have now questions. I'm afraid I will have to pick one because we don't have time
later
for two questions. So I picked the one by Andrew Brown. For the doubly excited helium results, what you described as hollow helium, it seems like a very simple model in the theory. Are there other effects in those results that aren't explained by that level of theory, or do you expect them to wash out in the FEL?
Yeah, so for the FEL, the problem with theory is in fact the following. It's really the fact that we do not have a perfect characterization of our FEL pulses. So every pulse looks different. And so at this stage, it's not possible for that reason to do a precision comparison, I would say, with theory. As soon as one would do this experiment with very well-defined pulses, for example, at Fermi again, problem at Fermi is the bandwidth is really small. So what we would need is really a sort of attosecond Fermi. If we have an attosecond pulse with a broad spectrum, a high intensity, this would be the ideal case for doing a very nice precision comparison with theory to see really whether we capture the full dynamics, because it's an interesting system. You drive 2 electrons and the double excitation is only possible because of electron correlation. So it's a very nice test case for really our understanding of the full theory in fields of electron-electron correlation.
Thank you. So we have to move on. Thank you, Thomas, for your talk.
Sure, thank you.
The next talk will be given by Lars Madsen from Aarhus University, and he will be talking about tunneling, many electron polarization, and non-dipole dynamics.
Yeah, good afternoon, everybody. I'll start by sharing my talk here. So, this is the title, you already heard that one. And the motivation for this work is that it's interesting to think about if it's possible to go to a description which is accurate and still easy if we have to deal with more than a few electrons. And the fact is that it's very difficult for us with the current theoretical methods to describe the time-dependent non-perturbative driving of a multi-electron system. So this is question number 1. I want to address that one. And question 2 is related to this because when we formulate theory, we tend to base our developments on certain approximations that we do not always check whether are valid or not. And one of them is, for example, the electric dipole approximation. And I want to discuss how to deal with situations where this electric dipole approximation breaks down. So that's the agenda. Specifically, I will go through these 3 parts here. I want to give a status on the formulation and the numerical implementation of tunneling theory. And this is, I think, very relevant for this network because this can now be applied to large molecules with many electrons. And then I want to show how multi-electron polarization effects may lead to a simplification of the response of a many electron system, which is then making it possible to formulate an accurate, effective, single active electron model. And in the end, I want to touch upon certain aspects of non-dipole strong field interactions between matter and light. Now, first about tunneling theory. This is a little bit review type topic. It's based on the papers given here in this slide, and they are clickable, so you can look them up. So anyway, as we know, if the timescale of the variation in the external field is much slower than the natural timescale of the electron motion, it can be an accurate, fairly accurate approach to deal with not the full dynamic problem, but with the tunneling problem, which I've tried to sketch here, where you have the tilted potential and you have the initial state here leaking out of a potential barrier. And traditionally, when we derive theory for this type of problem, and if we're interested in analytical theory, we are concerned with the matching of this bound state wave function with an outgoing wave here on the other side of the barrier. And some years ago, we formulated the weak field asymptotic theory in this type of representation where we focused on this tail of the bound state. The nice thing about this theory is that it can deal with molecules, and in particular with molecules that have dipoles. And I collect some formulas here on this slide. I need to do this because this will highlight the difficulty with typical tunneling type approaches. So in this theory, we have a partial ionization rate, which is a product of two factors: a field factor, this W here, and a structure factor, if we ionize, in this case, from a particular orbital. The field factor is fairly simple. It depends on a parameter kappa, which relates to the ionization potential, and it relates to the field strength. And there are some prefactors here which can be evaluated if we know the field and the kappa, and we know these guys up here, which are parabolic quantum numbers, and they typically 0. So that's fairly simple. That everybody that does a tunneling theory can get this one. Now, in this theory, the information about the system is more on this guy here, which is called the structure factor. It has information about the dipole of the system, and it has this thing here, which we call the asymptotic coefficient, which again involves some prefactors in parabolic coordinates, and then a projection of the ionizing orbital on well-known wave functions in the asymptotic region. And this here is now a key point, because when you formulate a tunneling theory based on this tail representation, you will end up with something that has to do with how does the orbital look like at large distance. And now in this network in general, we're interested in going to larger systems. This means that I need to have some good description of the ionizing orbital at large distance. And this, as we know, is very difficult using, for example, standard quantum chemistry software, because they are all based on expansion of the orbitals in Gaussian type orbitals. And Gaussian type orbitals have difficulties capturing the asymptotic part of the wave function. So therefore, we're led to the consideration whether it's possible to somehow reformulate the whole theory. So, okay, so this is a slide with a lot of text, and those who want to look it up on the web later can now read this. It's just what I just said about thinking about another way of formulating the theory such that we don't have to have an accurate description of the tail of the wave function. It would be nice if we can have a theory which depends on accuracy where the Gaussian type orbitals have weight. And this is possible, and this is what we have derived over the last 3 years or 4 years. And it's not maybe so difficult to understand that this is possible, because we know from scattering theory, for example, that we can get, for example, information about a scattering event from phase shifts, which is kind of a tail property. We also know that we can alternatively get scattering information from a T-matrix element green function type methods, which is an integral property. So also in this case, it's possible to formulate a theory which involves an integral of the orbital with some known functions, and this is what we want to have. And now I will just show you an example where we took a biphenyl system shown here, and we then varied the dihedral angle, that is the angle between the two benzene rings. And then here we have, as a function of this dihedral angle, we have this structure factor, and we have rates at different intensities from different orbitals in this molecule. And it's not, I mean, here the point of this view graph is not to understand that particular result. It's more to show to you that it's now possible to calculate the structure factor for basically any molecular system that can be treated by standard quantum chemistry methods. And I think this is important because the tunneling process is used as the initial key process in much of strong field physics. So that concludes topic number 1. Now I go to topic number 2. This is about multi-electron polarization. Some of you know that I have spent quite some years trying to develop many electron time-dependent methods. We developed something called time-dependent restricted active space self-consistent field method. We're still working on that. It's very difficult. It's nice if we can do a simpler job, trying to do something where we model the dynamics and if in fact try to get a single active electron approximation. And this part of the talk is based on those two works listed here. And the point I want to give here is that in strong field ionization, and if we just pull one electron out, there are two dominant effects from multi-electron polarization. The first one is that in addition to the, say, long-range Coulomb interaction and the external field, we have this one here, which is the permanent dipole potential and the induced dipole potential, where this induced dipole is related to the polarizability of the cation. So that's one effect in the asymptotic region. The other effect is that when you apply the external field, all the other electrons polarize, and they in fact set up a field in the inner region that counteracts the external field. So effectively in the inner region of this system, there will be no laser atom interaction. And this means that we led to the consideration of these types of potentials. Here I have that this is an illustration of a field-free potential. This here is an illustration of a potential in the presence of the field. And then I have two other potentials. I have one where I include here by the crosses the induced dipole potential above a cutoff radius. And in here I don't have any laser matter interaction. And this one here, I take a simplified one where I don't even consider the exact form of this induced dipole potential, but just switch off the interaction from the field-free potential. So what we do is that we choose a cutoff radius for this switching off here, where the core polarization cancels the electron laser interaction. And then with this type of physical ideas, we go to our time-dependent Schrödinger equation solver. We write down the interaction in the length gauge. Now it's just a matter of including the polarization term together with the normal length gauge interaction, as you see here, when the radius is beyond the cutoff radius, and the interaction due to this cancellation of the interaction in the inner region due to the polarization of the remaining core electrons, we just put it to 0. And in the other model down here, we just switch off and do not take into account the exact form of the polarization. So with this, we have tried to look at some molecules. We have looked at CO and more recently on OCS. And in CO, you have a calculation here, which shows you the ionization yield as function of orientation angle. When the orientation angle is 0, the main lobe of the electric field point from the C atom to the O atom. And in the left-hand side here, we have not taken into account the multi-electron polarization effect. And in the right-hand side, we have taken into account the multi-electron polarization effect. And you can see it's completely different, a prediction. And the one here to the right, where we include this effect, is consistent with the experimental results. We have also checked whether it's important to take into account the correct form of the polarization asymptotically, or maybe it's enough just to switch this off. And this is what is shown in this view graph. So for this particular molecule, it's good enough just to switch off the induced dipole potential in the outer region. For other molecules, it's different. And we also looked at some photoelectron momentum distributions. We have here, we have to the left, we have including full multi-electron polarization, and to the right, we just turn off the multi-electron polarization beyond the cutoff radius, and they look very much the same. So certain observables are not super sensitive to the exact form of this multi-electron polarization term. This situation is maybe different for other molecules, and we have new results that we just put on archive. You can look up here for OCS. So that finishes, in fact, the second topic. And now for the remaining part, we have time for this discussion of non-dipole effects. And here is the reference, which has some of the details. And okay, so now in the dipole approximation, what it is, it's that we neglect these type of propagation factors in the description of the electromagnetic field, where this KL here is the wave vector of the light, which of course depends of omega, the angular frequency of the pulse and the speed of light. And in the dipole approximation, we put this factor equal to 1, which amounts to assuming that the variation of light over the atom, or in fact over the extent of the bound state orbitals in the atoms or in the molecules, is very small, and that's why we can put it to unity. Of course, it's been known for a very long time that this is an approximation that breaks down if now the angular frequency here is large, naturally. And typically, you see a breakdown experimentally as a lack of forward-backward symmetry with respect to the laser propagation direction. And now, during the last, say, 6-7 years, we've seen a number of experiments performed at high intensity, low frequency light. And some of the experimental results are listed here, where they also see a breakdown of the dipole approximation. So it's interesting to look at this, and I think I mean, if we can identify non-dipole effects in larger systems, there are, of course, certain observables that are, say, 0 if we just do the dipole approximation, but non-zero if we do the non-dipole approximation. So we have a new parameter window to work in and to look at all the things we like in terms of dynamics, time-resolved issues, and so on and so forth. So that's the motivation behind this. To understand why the dipole approximation can break down at high intensity and low frequency, you can just look at the laser-induced quiver velocity, which scales as field strength over angular frequency. And if this one is fairly large, the field strength, and if the angular frequency goes down, this becomes large, and it can be non-negligible compared with the speed of light. Now, conventionally, what we do is that you can, for example, tailor, expand the laser matter interaction in order of 1/c. But if you do that, it's fine. There are some issues with that. But what I want to do is I want to come more from the strong field side and see if I can do some extra analysis, some accurate approximations to that conventional approximation that simplifies the problem. So that's just the idea. And this is what we have done, and we have written down some Hamiltonian. Other people have done the same before us, which is attractive for numerical and analytical modeling. So this is now a standard stuff here. We have the minimal coupling scheme. So P goes to P minus QA, where Q is the charge of the particle, and A is the vector potential. And I have here eta expressed in terms of the angular frequency and the position, the propagation direction x. The vector potential in this case is like this. If this epsilon here is 1, it's circular polarized light. If epsilon is 0, it's linearly polarized light polarized along the z-axis. If I do a first order expansion of the vector potential, I get the 0 order term, which is the normal dipole term, and I get a correction term here. This correction term here now gives, in fact, 2 terms, because I have a variation in the carrier, but I also have a variation in the envelope. But if we have certain number of cycles in the field, this one here is not very important. In any case, the total Hamiltonian reads like this. We have the normal dipole term, and I have a correction here, which is the correction to the dipole vector potential times P. So this guy up here mainly. And then I have the dipole vector potential times the correction to the dipole vector potential to first order and 1/c. Okay, so if we just look here, we know how to deal with this one. This one here is a little bit complicated from a theoretical point of view because you have P here. So this is in momentum space. And this A1 is, as you see up here, in coordinate space. So this guy here mixes coordinate space and momentum space, and that's not very attractive to deal with for numerical issues. Whereas this guy over here is just the spatial independent vector potential, and here you have the correction, which is spatial dependent. Okay, so that's nevertheless what we have. Okay, this is now summarizing what I just told you. And I want to stress here, it would be convenient to introduce accurate approximations that bring the Hamiltonian on a form which does not include products of X and P operators. And to do that, we just think back on very simple physics and consider classical equations of motion and introduce approximations to those ones, and then we construct the corresponding Hamiltonian. So that's the schedule. So here you have a Newton's equation of motion with including full retardation in the E field and in the B field. Then, of course, you can write down the same equation to first order in C. So this is this one here. But what we're interested in, and now comes the physics input, we're interested in the regime where the laser intensity is large and the frequency is small. So in that regime, it makes sense to consider the effect of the B field component along the E field induced motion. And this is the equation I write down here, which has now the E field, and then it has the Lorentz force along the dipole induced motion, which is written here, which comes directly from Newton's equation. So that's the idea. And then there are some particular issues that are written here in a rather maybe strange form, but this is to remember that these non-dipole effects in fact depend on polarization. So if we have, for example, circular polarized light, the laser-induced dipole motion is aligned parallel with the B field. So I think it's also important here to point out that there's a polarization-dependent sensitivity to non-dipole effects. And here, so now it's time to see how these different theories work. And it's shown here in these 4 graphs. And let's see. So here, here you have X and X dot. That's the position and the velocity along the polarization direction. This is now for a linearly polarized field. And then you have X and X dot. That's the position and the velocity along the propagation direction. And we have done a simulation here where we have started classical trajectories from the exit point, and we have used a field which is comparable to one of the experiments, and we look for 10.5 cycles in time. And then you have 3 curves, and let's see, the dotted yellow curve, that's the most accurate one, and the full blue curve is the conventional 1/c expansion. And then you have the long dashed red curve, which is the one I would argue in favor for. This is the one where the effect of the B field is included along the dipole-induced trajectory. And you see here, along the polarization direction, they're all doing fine, but along the propagation direction, the dashed one is doing better than the conventional one, and it's because you have some dependence in the blue one that when X becomes large, it becomes less and less accurate. So at least this illustrative classical calculations suggest that it's accurate. It can be accurate to use this form. When we have that, then the idea is to take that classical equation of motion, and then now you have to find the Hamiltonian. This is the exercise. Now we have to find the Hamiltonian that when you apply Hamilton's classical equations of motion to that Hamiltonian, you get the approximate classical equations that we just looked at. And if
2 minutes left.
Yeah, if you start with this one, this is what you will get. And this is what we call the strong field, the non-dipole strong field approximation Hamiltonian. In this case, you have a term here which depends on X and one that depends on P. So we call that mixed gauge in accordance with the tradition in strong field physics. And we can transform the operators and bring the stuff into either full velocity gates, non-dipole strong field approximation, Hamiltonian, or length gates form where we have modified vector potential with two terms, including modification, and the E field including modification. And in the long pulse limit, we can, for example, look what is this modification, and it's related to a typical radiation pressure effect. You can also write down the Volkov wave functions if you like, and they are known analytically, and you can get effects in terms of a shifted Prandtl-Motiv potential. And I just want to highlight here that we did recently something on laser-assisted scattering, showing that the non-dipole effect here enters, and this is, I mean, for the experts, that you have these type of expressions involving arguments in a Bessel function, and the non-dipole effects predicts significant cross-sections in geometries where there is no cross-section if you work in the dipole approximation. And that's discussed in this particular paper. And also with this Hamiltonian, we can predict shifts in the propagation direction, which are the same as people have observed, for example, this recent Nature Physics paper here. And this leads me to the summary. I wanted to give you a status on the possibility of determining accurate tunneling rates for any molecule that can be treated with quantum chemistry methods. That was the first part of the talk. We are currently working on implementing this technique in the new distribution of games, so it will hopefully come soon. And then I discussed physics related to multi-electron effects and showed how we could use some physics ideas to design an effective single active electron model potential that could predict observables that could not be predicted with kind of standard single active electron models. And then in the last part, I presented some discussion of a possible simplification of the way we can deal with non-dipole effects in a strong field setting. Thanks for your attention.
Thank you very much for your talk and all your interesting results. We have already questions. The first one is by Eva Lindroth, and she asks, this method to account for polarization by just turning off the field in the inner region, does it require that you have really many electrons? Have you compared it to ab initio methods for atoms, for example?
No, we have not. We have not had the chance to do that. So the problem is that what we have done here is that we have entered a regime where ab initio methods are very difficult to apply, right? Because we have a strong field driving at 800 nanometers, and we can maybe deal to some extent with helium, which is anyway very little polarization. It has very, very small polarizability, so the effect there would be small. So what we are doing is that we are trying to pick up experimental results, typically in alignment or orientation dependent total ionization yields. So we pick up those results and we try to explain them with this. And we have done that for CO, and we just found that it also works for OCS.
Mm-hmm. Thank you. So are there any other questions? If not, I might ask one. So my question is maybe, let's say, a little bit naive one, but I would like to know your perspective. So do you think there could be a possibility to extract effective potentials for a single active electron calculation out of experimental data, so using some holographic measurement schemes? So of course in the case where only one electron really significantly contributes to the dynamics.
Yes, I think I mean, I've not given it much thought, but I think it should be possible. I think in fact there are in that direction, there are experiments on dimers. I think, I mean, now I think I remember some experiments from Reinhard Dörner where they extracted information about the effective potential when you break up a dimer. So your question is somehow in that direction, but now of course related to the ultra-fast electron dynamics. Maybe, but I don't know. I mean, I cannot just say yes or no. So I think we all have to think more about that. But it's certainly an interesting perspective. Thanks.
Mm-hmm. Thank you. So I don't see any questions popping up, and in view of the fact that it's almost 5, I thank you again for your talk and the questions, or the answers to the questions actually. And we move on to the final talk of this session, which will be given by Agnes Vibok. She will be giving a talk on few femtosecond electron and nuclear dynamics in the ozone theory and experiment. So the word is yours. Agnes, are you here? Now we can hear you.
And then can you see my talk?
Yes, we can see it.
Okay. So
but we see a split screen, so maybe you somehow managed to just show your talk, because right now we see your talk and the Zoom meeting as well.
Ezt megint ugyanott lesz.
Jobb oldalit választ ki.
Ezt. And you see that? The same?
Yes, unfortunately it looks the same again. Now it's better.
Do you see it?
Yes, we can see it.
Okay. Thank you very much. Good afternoon. I would like to thank to give us a possibility to talk about our recent work. It is not so recent. What I would like to report here is a protocol to simulate theoretically a pump and probe coupled nuclear electron dynamics for the medium-sized molecular system. And then this will be a result for a long collaboration among several theoretical and experimental groups. So that's okay. The short overview. At first, I talk about a little coupled electron and nuclear dynamics and molecule nuclear dynamics. Then the time-dependent part, time-dependent electronic wave function, probing the electronic wave function, and finally the experiment. Okay. And then it is known that electron dynamics in molecule, in most of the time, I strongly couple it to nuclear dynamics, and proper theoretical description of them in polyatomic molecule is a challenge. It is well known. And then we targeted medium-sized molecules, which are not big, not diatomic, 3, 4, 5 atoms, and then we wanted to develop a protocol system, but our sample system, what I will show here, will be the ozone molecule. What we will do, we try to, at first, we try to do a Born-Oppenheimer type separation between the nuclear motion and the electrons. We will treat the nuclear dynamics very accurately by using a very accurate MCTDH method and using accurate ab initio potential energy surface. And then we will build up the electronic wave function by using the nuclear coefficient, time-dependent coefficient, and then we try to probe it, and finally I will show the experimental results. So the sample system, as I mentioned, what we choose was the ozone molecule. So that, as you see, the ozone molecule is a very interesting, this molecule has a very interesting electronic structure. There are 4 different energy regions, the Wolf, Chapois, Huggins, and the Hartley. So our first idea was to do a pump and probe numerical experiment also and real experiment, and then to create a coherent superposition of several electronic states in the molecule by a pump pulse, which would be a attosecond, of course, and also to probe this electronic wave packet by another attosecond pulse. This was the original aim. And at the very first time, we wanted to include in the superposition of the electronic wave packet the ground state, the Chapois state, the 2 Chapois states, which are coupled non-adiabatically, and also the B state, the Hartley. So in this case, it would be involved 4 electronic states in the electronic wave packet. But the problem was that it turned out it was easy to do it theoretically, but not so easy experimentally. So the aim was that to excite the Chapois band by a near pulse, and with the third harmonic of it at the same time to excite the B state and to create a coherent superposition. But the problem was, from experimental side, that the transition dipole moment between the ground state and the Chapois state was much smaller than between the ground state and the Hartley state, so that in order not to wash out the coherence in the results, they should compensate it with the intensity. But it was a big, hard task. This was what the experimentalists, our experimental collaborators could not do. So finally, we came to the conclusion we should make a simplification, and instead of including 4 states in the electronic wave packet, we just included 2 states. This was the ground state and the Hartley. And so what I show here, that we started a simulation, different steps. I will show throughout the procedure what we did. And throughout the procedure, we used these parameters. For the pump pulse, we used deep UV pulse, 260 nanometer. The intensity was 10 to 13 watt per square centimeter, and the pulse length was 3 femtosecond. And then the probe stage, we used attosecond pulse, half femtosecond, 500 attosecond pulse, XUV pulse, and the energy was 95 eV. So this was the parameter, these were the parameter what we used throughout the numerical simulation, but finally we repeated the whole stuff with a completely new parameters, which can be available also for the experimentalists. I will show it. But these results will do with this. So we started from the total wave function. We built up the total wave function as the usual, as a product of the nuclear wave packet and the electronic wave function. We can put it into the time-dependent Schrödinger equation, and then integration, if we perform integration over the electronic coordinates, we arrive to the well-known nuclear dynamical Schrödinger equation. Here you can see the Hamiltonian contain the nuclear kinetic energy, the potential energy, and the coupling. As we dropped the Chapois bands, we had no non-adiabatic coupling in the calculations, only the light matter coupling. So that this equation, what we had to solve during the simulation, we used, as I mentioned, the well-known, very accurate MCTDH multi-configuration time-dependent Hartley method to solve the nuclear Schrödinger equation. This is a very accurate method, and it's very accurate up to 25-30 modes. It's the wave packet also contained the relative phases between the electronic states. So that by using this this nuclear wave pocket, we could calculate the time-dependent density operator. As usual, this is the operator, the time-dependent density operator, and by using, we could calculate the density matrix, and applying and using the diagonal elements of the density matrix, we could calculate the state population. So this is the population on the I states. You can see here that by using our pampas, we can populate the Hartley states up to 40%. You see it here. This is the electric field that we used. And then by using this nuclear density function, we also could calculate the two-dimensional the nuclear wave function. We could calculate the two-dimensional nuclear density function. We make a integration over the theta. We had two coordinates, the R1 and R2. These are the two bond lengths of the system. And then what I could show here, this is the snapshot of the time evolution of the nuclear wave pocket density along both OO bonds. You see here, this is R12, another R13, and this is the diagonal. And then you see here at 4 femtosecond, this is the wave pocket density at the Frank-Condon area. And as the time goes by, we can see that the wave pocket, the nuclear wave pocket, divided into 3 parts. 2 parts move along the bond distance, and the third in this diagonal direction. And then it's very funny that we found, you can see it here and here, that at certain point when the pump pulse is off, some population come back again to this Frank-Condon region. Somehow it means that we see it as in a coherence revival when we calculate the electronic coherence. So that we also calculated the local population density. You see here at the Frank-Condon point that there is a large population, and then decay, and again come back a little. And then similarly, we could calculate the relative electronic coherence still from the nuclear wave pocket, from the accurate nuclear wave pocket, by using the off-diagonal elements of the density operator, the density matrix. With this expression, we could calculate the relative electronic coherence, and you see here the coherence build up very fastly, then remain around 5 femtosecond and start to decay again and come back again 15, 20 femtosecond. And we could see the fingerprint clearly, this effect on the time evolution of the nuclear, two-dimensional nuclear density map. So this was what we found from nuclear dynamical side, and we turned to electron dynamics. We calculated everything again in the Frank-Condon geometry by electronic side. So we calculated with the MolPro package the ground state and the ground state wave function, and also the Chapois wave function, and we could calculate the electron charge density with this expression, and also the transition density between the different electronic states with expression. So by using these two expressions, we could calculate the time evolution of the excited differential electronic charge density at the Frank-Condon geometry. So there is some sense, because we could see from the very accurate nuclear motion that the molecule remain in the Frank-Condon region at the first 5 femtosecond. So you can see here the quantum beating, you can see here the charge oscillation, hole and the electron oscillate back and forth between the X and the B states. So that's what we found. And then we had a main task to probe somehow the electron dynamics in the Frank-Condon region. But to do this, we should very short laser pulse. That's what we couldn't do. Our experimental collaborators couldn't do. So we went a little further and we calculated the Dyson orbitals because they are good predictor of the ionization probability. So we ionized the system and we went further in time. So we calculated the Dyson orbital. This orbital correspond to the transition amplitudes between the n-electron neutral system and the n-1 electron cationic system. So we can calculate with this expression. And then we can combine it with the time-dependent nuclear coefficient obtained in order to obtain the time-dependent Dyson orbitals. So we calculated the time-dependent Dyson orbitals as well. And then from this, we could calculate the Dyson norms. And the Dyson norms is well known that are good predictors for the corresponding ionization yield. We published it in. So that with this expression, we could calculate the stick spectra of the system. So it means that you see here what we did. We ionized with a probe pulse the molecule, which is in coherent superposition. Electronic wave pocket is a coherent superposition of the X and B state. So in the ionization, during the ionization, the ionized electron can come from either from the X state or from the B state to the to the corresponding cationic states. So we included 19 cationic states in the calculation. One is the ground state and 18 excited cationic states. You see here the corresponding relative intensity peaks. So it means that this line comes from when the molecule is excited from the X state to the 19th cationic states of the cation, and so on. And we convolve this stick photoelectron spectra by a Gaussian function, and we obtain the approximate photoelectron spectra as a function of time delay. So this is a very short time period, and then in this picture we can see clearly the depletion of the X state and somehow the production of the B state. But we went further, and then with a new theoretical so we extended our theoretical group by Professor Piero de Cleva from Trieste, and then we could calculate not only the time and energy resolved photoelectron spectra, but also the angularly resolved photoelectron spectra. So we had a nice expression to calculate very accurate results. And then finally, our experimental collaborators asked to repeat everything from the beginning with those parameters who are also available for them, and which parameters they can manage experiment. So finally, the pump pulse was deep UV pulse, 268 nanometer. The intensity of this pulse was 1.8 times 10 to 12 watt per square centimeter, and the full width at half maximum of the pulse length is 10 femtosecond. So it's short. So comparing to our original aim, when we wanted up the attosecond from both pump and probe side, we could not do this. And from both probe side, we used the XUV pulse, 99.5 EV. The intensity was 10 to 12 watt per square centimeter, and the pulse length is 1.7 femtosecond. And what our experimental collaborators obtained, this is the result. In the first panel A, you can see in left side here in red, this is the photoelectron spectra of the ozone molecule when only just the probe pulse is applied. No other, the molecule is in stationary state, not in a coherent superposition. So you see here the spectra. And you can see here 4 different regions. The first, the bottom, and the middle corresponding to the electrons which comes from the X state. The last one corresponding to electrons which comes from the Hartley states, and the second region corresponding to electrons which come from the oxygen molecule. So that in a second panel, in the panel B, you can see the production of the X state somehow. So these are the electrons in these curves, which comes from counted electrons, which comes from the X state. At the beginning, you see that it is constant, then start to decrease around 20 femtosecond. This is the time there is a depletion in the X state. You can see the fingerprint of this here and here. It means that in this region, the electrons can go to the B state, and then from the B state, one part of the electron can ionize. You see the fingerprint here, and the other part can dissociate and then form O2, oxygen molecule, and then the electrons here comes from the oxygen molecule. So this is a very complex situation, because we should write the dissociative ionization for a system which has many electrons, and then it's not easy to make a distinction between the electrons which comes from the oxygen molecule and which comes from the X state. So that finally our experimental collaborators obtained these results for the X state and for the O2 production. And the next figure, you see here the production of the B state. So these are the photoelectrons which comes from the B state, from the Hartley state. And then this is the experimental results, and this is the results what we calculated from the beginning with the new parameters. You can see here, so this is a angle resolved photoelectron spectra. The theta means the angle between the time of flight spectrometer, photoelectron spectrometer, and the polarization axis of the probe pulse. So that we saw some similarity between the shape of the figure produced by the experimentalist and then our theoretical figures, and we could see some similarity with the shape of the, if you remember, the coherence revival picture, but this was not enough. This was not enough convincing for the referee, so it's also finally it was not clear. It was not, because if you see that it's a long time here, so that it's there is a plateau and then decay and again a plateau. So we could see some fingerprint of the coherence revival, which can be reflected in the photoelectron production of the B state, but it is difficult, very hard to make distinction, because in that region, time region 30, 40, there is a very hard dissociation as well. So finally, this is the outcome. So this is the experimental outcome of our numerical simulation. We plan to do it. We plan to maybe make it more accurate from theoretical side, because in this simulation we assume isotropic ensemble. We can make also alignment. So there are some, and also we should move somehow from the Frank-Condon area in the electronic structure side, but these are still difficult tasks, and then probably our experimental collaborators doesn't want to make more effort on that subject as well. So this is what I would like, and then I would like to mention the collaborators from Debrecen University, Gábor Halász. We have a very strong collaboration, and we continue it with similar subject, but other system with Benjamin Lazor, Aurelia Pervot, University of Montpellier, Fabien Gatti, David Lavergnac, University of Paris, Michael Rope, he helped us to modify the Gaussian code to calculate the Dyson orbitals. Professor Piero Decleva from University of Trieste, and from experimental side, the whole experiment, the whole idea came from Ferenc Krauss. He was involved in the beginning, and later on he was not so interested in that subject, and then the main work of experimental work is of this is Reinhard Kienberger and his two clever PhD students Tobias Latka and Michael Jobst, and several other experimental colleagues were involved also in this job. So. And then I would like also thank for the grant and financial support, and thank you for your attention.
Thank you very much for your talk and all your interesting results. So the talk is open for questions. So far, I don't see any new question popping up. So I have a question on your final data, where you showed experimental results with a pronounced peak and the theory results that quite strongly varied with the angle theta. But I guess in the experiment, they did not align the molecules. So in the experiment, the experimental trace would be an average over all those theta that you have shown separately in your theory data.
I think they aligned the molecule in the experiment.
Okay. In which direction did they align it?
Yes, that's what we didn't account it for in the simulation. So in the simulation, we just assumed, as I mentioned, isotropic ensemble. So we had no assumed alignment, but they did, yes, also.
So the experimental data would then correspond to your theta equals 0 results? Or?
Yes, because the experimental facility was on that line. Yes, theta equals 0. So you see the black curves on the B panel. Yeah, but we made a calculation for several other theta. Yes.
Mm-hmm. Thank you. There is one question by Morgan Bacher. Analyzing in detail your nuclear dynamics simulations, could you see some asymmetry in the time-dependent yields of the two dissociation channels, which would be a signature of the oscillating electron-hole dynamics?
Asymmetry. Here, do you see this? I don't remember this, that we could see some asymmetry in the two sides. We didn't realize this kind of picture in the.
We were not searching for it.
Yes, but maybe we can check it. But so that which was interesting, and so we at first we did the whole numerical simulation when we involved the 4 states. And then we published nice results. And finally, when we went to this simplified situation, only included 2 electronic states, only in that case we found this revival. So there is no revival when we had the 4 states included in the electronic wave packet. So this coherence revival came back only just when the simplified situation was accounted for.
Mm-hmm. Thank you. Are there any other questions? I don't see any, so let me thank you, Agnes, for your talk. And I would like to thank all the other speakers as well of this session. I want to remind you that in principle all speakers are available after this session in the Meet the Speaker sessions, but also starting with 5:30, so in, let's say, 1 minute, there is in parallel a poster session which lasts until 7:30. So you are of course welcome to also attend the poster session and look at the posters and have a chat with the presenters of the posters. You can also meet them at the meeting hub of the platform. And with that, I thank you all for attending the third session, and I wish you a nice evening. Goodbye.